All right, so I want to talk about the difference today between what I'm going to call increments and differentials. So suppose you have 2 points x1, y1, and x2, y2 on like the graph of a function like over here. So then delta x refers to the difference between the x coordinates, x2 minus x1, and delta y refers to the difference between the y coordinates. So over here, delta x refers to this horizontal distance, and delta y refers to this vertical distance. And so in this particular example, I have the points 1, 0.25 and 4, 4. I'm using this function f of x. So delta x is 4 minus 1, which is 3, and delta y is 4 minus 0.25, which is 3.75. Now, since y equals f of x, another way I could think about this is I could say x equals 1 and delta x equals 3. So then delta y is equal to f of x plus delta x minus f of x. So I'm now thinking of, you start at a value x, and then you shift delta x over, and you figure out how much y changes. So that here, my function f of x is, of course, x squared divided by 4. So what you get is 4 squared over 4 minus 1 squared over 4, since x plus delta x is 4 and x is, of course, 1. And so then that is 4 minus 1/4, which is 3.75. So now suppose instead that I just had some different arbitrary function, like maybe f of x is the square root of x. And I want to find delta x and delta y from x equals 2 to x equals 6. Well, delta x will simply be 6 minus 2, which is 4. But to figure out delta y, I'm going to calculate f of 6 minus f of 2. And that's going to be the square root of 6 minus the square root of 2. And what is the square root of 6 minus the square root of 2? Is about 1.035. All right, so that is exactly what's happening. So what I'm going to do to approximate, so these are increments. So now down here, I'm going to talk about a differential. And so there's two differentials. There's dx and there's dy. So dx is just another way of saying delta x. It represents a change in x. But the idea is that dx is small. Sort of an instantaneous change in x. And so then dy is then delta y when x dx equals delta x is small. So if you think back to dy dx, remember, was just another way of saying the derivative. And so dy dx is very roughly equal to the change in y over the change in x, and they get closer as delta x gets closer to 0. So we can think of the derivative of a function as approximating that secant slope, that change in y over change in x. So since dx I defined to be delta x, the differential of y should approximately equal delta y, but specifically dy dx is exactly equal to f prime of x. So the differential dy is defined to be f prime of x dx. And so in my specific example here, f of x was a square root of x. So let's see, which is x to the 1/2. So by the power rule, f prime is 1/2 x to the negative 1/2, which is 1 over twice the square root of x. So dy is 1 over 2 root x dx. Going back to f of x equals x squared, which is the business over here, there you get dy is, again, f prime of x dx, which is going to be 2x dx. Now, what does that mean? What that means is, so at my specific, remember we had said x was 1. So if x is 1, dy is just 2 dx. And so what that's saying is that if you take a line, so I'm going to go back over here. So draw a line. With slope 2 at the point 1, 0.25. And so that should be the line y equals 2 times x minus 1 plus 0.25. And if I plot that, oh, right, so it was actually x squared over 4. Oh, man. So that's divided by 4. So this is not 2x, it's 1/2 x. And so then this is 1/2. And this is 1/2. All right. Like that. There we go. So now I actually got the right tangent line. Well, I'm glad I drew a picture of that because I can see the stupid mistake I made. So the idea here is the tangent line is approximately equal to the function at this point. So for example, in this very specific example, we had delta x was 3, so then dy is 1/2 times dx, but remember that delta x and dx are the same thing, so this is just 3/2. And so what that's saying is if you look at the point 4, 0.25 plus 3/2, call this 1 plus 3 just to make it explicit, you're going to get this point here on the tangent line. And so the change in the y value of the tangent line is approximately equal to the change in y for the secant line, or for the original curve. And so just to make this more explicit, I'm actually using a slider here on the graph. A represents delta x. So if A represents delta x, then what I can do is instead of calculating like this, I can say dy is 1/2 of whatever my number A is. So then what I can do is I can do the point 1 plus A, comma, 0.25 plus A over 2, and I'll just tweak this. I'll make this 1 plus A, f of 1 plus A. We'll get rid of that. I keep the tangent line, I get rid of that. So you can see here the points are far apart, but as I make A closer to 0, those 2 points converge to each other. So line 7 here will be delta y. So delta y, remember, is going to be f of x plus delta x minus f of x. In that case, that's going to be f of 1 plus a minus f of 1. So it's the exact change in y from this point to this point. But dy is just 1/2 of a, so I can just write a divided by 2, and that's the approximation. And so you can see that 1a is large, that difference is pretty big, but if I make a smaller, they get really close together. And so the big idea here is that you can use the differentials to approximate the changes in the value of y. So in another video, I'm going to just work a couple examples of me calculating all this stuff by hand without the aid of a graph, and then I'm going to show a couple applications of it.